Well, hey everybody, this is part two of my discussion of thermodynamics. This is actually the last lecture that has any kind of new content in it, so this is kind of a finish line, so you should feel pretty accomplished if you've gotten this far. And as I'll talk about in a moment, even though this lecture is fairly dense in terms of analyzing thermodynamic cycles, which we'll talk about in a second. It's for your own good because there's a question on the homework that deals with this, and I want to give you some of the tools for being able to do those problems. Last time we talked about the different thermodynamic processes. So these are isobaric, constant pressure, isothermal, adiabatic, and we talked about how you only get adiabatic if you have very rapid compression or very rapid expansion. Then isochoric is if you have some kind of sealed container. The container is not expanding or contracting or anything, and you're just adding energy to that system, or maybe letting it maybe letting it exchange energy with the outside ambient air or whatever. Today we're going to talk about thermodynamic cycles, and this is going to involve combinations of these processes. So there's still only 4 processes, but you can combine them together to do a couple of things and then start where you get back to where you started. And so to make an engine, for example, you have to have some kind of a thermodynamic cycle. And it turns out that the most efficient engine that you can make, which is called a Carnot engine, C-A-R-N-O-T, which you can find in the book, that involves 4 thermodynamic processes. So 2 of those are adiabatic and 2 of those are isothermal. That turns out to be the most efficient engine of them all. I'm actually not going to talk about that one. But so you can have thermodynamic cycles that the main thing is getting back to where you started, so you can do the whole thing over again. And so you can do that in 4 steps. Presumably you could do it in 5 or 6 or 7 steps, something like that. The smallest number of steps that you could do would be 3 steps. So I'm going to focus on 3-step thermodynamic cycles today. And there's a question on the homework that's a 3-step thermodynamic cycle, and so I hope this helps you to answer that question. So this is the simplest engine that I can think of. So we've got a sealed container here. We have some sort of gas that's inside of this sealed container. I'm saying that it's helium, but if I wanted to, I could change this to air or any kind of other gas. It doesn't really matter exactly what kind of gas it is. And so the idea is that this piston is going to be compressed, going from here to here. It's going to be compressed. And then we're going to turn on the laser, so like that. And that's going to heat up the gas inside of this thing. But while the laser is on, we have sort of a pin here that's holding this plunger thing on. And so we've increased the pressure there. And then we're going to turn the laser off, and we're going to let go of that pin, and it's going to expand out like so. And so the first question is, which process is happening at each of these 3 strokes of this engine? Or you could say each of these 3 phases or steps or whatever you want to call it. So, but with engines, we typically say stroke. So if you think about it, this first step, the pressure is constant. As the little plunger compresses, the pressure does not actually go up. And so this first step has to be isobaric. The second step, when the plunger is compressed and we have the laser that's turned on, and we're making the gas inside of it hotter and hotter, that is, we're not expanding or contracting, so the volume is constant. What do we call constant volume processes? Well, the answer to that is isochoric. And then the third step, which is an expansion step, I'm going to say it's adiabatic. Typically, it's not quite possible just to stare at this plot and determine whether it's adiabatic or isothermal. Typically, the question that you're reading will say, oh, by the way, this is an adiabatic expansion, or oh, by the way, this is an isothermal expansion. So for the next couple of slides, like 10 slides or so, let's assume it's adiabatic. We'll come back to the possibility that this is isothermal later. So now we have the three processes figured out. The next step is to think about the temperatures. And if you think about the system, there's three different temperatures in this problem. So we're going to start out with this temperature. I'm going to call this T warm. And so we're going to start out with this temperature. And our cylinder thing is going to compress. All right. And by the time it gets to here, it's going to be a different temperature, it turns out. And then we're going to turn the laser on. And we're going to get up to a much higher temperature, the hottest temperature of the system, T hot. And then as it expands, it's going to go back down to T warm, and then we can do the whole thing over again. So again, there's three different temperatures that are in the system. In terms of their relative, which one is the highest temperature, we're going to start with this temperature. There's also this temperature. It would make a lot of sense that right after you dump all the laser energy into the gas, that this is the hottest temperature. And then because it's adiabatic expansion, we know that that's going to cool here. So we know this is the hottest. This is the second hottest, and I'll talk about in a minute why this would be the coldest. But we get this sort of hierarchy of the temperatures in this situation. So let's talk about this first step, going from here to here. What's interesting is that it actually takes work to compress this piston, right? So something has to compress this piston, and which is annoying because we're trying to use this to do something useful. And as we'll talk about in a minute, the useful phase is sort of when it goes from T hot out to T warm. That's when things are moving. That's when we can actually use this to do something useful. But for this first step, we have to sort of apply a force to get this thing to go down the way that it does. Now, that's true. The question is there heat exchanged during this step in which it goes from, again, it's starting from here, it's going to compress down like so. Is there any heat exchange during that step or not? So I'll let you think about that for a second. And the interesting thing is that the answer is yes. And the reason the answer is yes is because if there was not heat exchanged, then this might stay at the same temperature, T warm, and if it's going to stay at the same temperature, and you're compressing the volume, then that is an isothermal process, and the pressure, instead of staying constant, would start to climb up because you've got a sealed container. There's gas that's trapped inside of here. Gas is very much higher density now that we've compressed the piston, yet the pressure is the same. The only way that this pressure can be the same as it was when the piston is out here is if the gas is cooled down. The only way for the gas to cool down is if it dumps this heat to the outside medium. So this piston is in sort of cold air here, or you could think of TC as maybe like room temperature or something like that. And my dog just sat down. And so TC is like room temperature. T warm is something that's warmer than room temperature but colder than the hottest temperature that the system gets up to. And again, the only way for this system, this engine, to go from here to here without increasing the temperature is if the gas cools down significantly. So yes, there is heat exchange because otherwise the gas inside of it would probably stay at the same temperature, or maybe even increase temperature if we were compressing it quickly enough. So yes, there is heat exchange. Yes, it cools down for sure. I think I just said all these things. So what's interesting is that you might say to yourself, well, wouldn't it be nice if we could use that heat to do something useful? Isn't that sort of a waste? We have all this like hot gas inside of the thing. Why can't we use that to get some more energy out of the system? Well, the answer to that question is that we could, but we have to get ready for the next step. And to do that, we have to cool this air down. Now, in a conventional automobile engine, for example, we would just let the air, we would just put it through the exhaust, we take in some new air. But for our purposes, we're just going to keep a sealed container. And so because we're doing that, the only way that we can do this is if we have that gas cool down. And having the gas cool down, it also helps to decrease the amount of force it takes to push this piston back to the place where the laser can fire, because it takes force to do that, right? We have to push it. And so if you allow the gas to cool down, that makes it easier to push that thing back to where where the laser can turn on, and we can do the whole thing over again. Now, an equation you'll sometimes see in units like this is this one. So Q hot is the energy that goes into the system. So in our case, this is the heat from the laser. And at the end of the day, the heat from the laser is going to go into the useful work that we're going to get out of this system. But we're also going to lose some of this heat to the ambient medium, which, in this case could be the room temperature air that this device is in. And so energy conservation tells you that the heat into the system, say from the laser, goes to useful work and stuff that is not so useful. But this not so useful stuff helps you to compress the piston so you can do the thing the next time. So a diagram that people like to show is this one, and this is a good diagram, I would say, is that there's heat into the system, and again, there's kind of a flow chart. Some of this heat isn't going to do anything useful, and that heat will just be dumped when we're in that compression phase. But some of it will be going to the network. And so we can figure out what the efficiency of this engine is by considering the ratio of the net work to the heat that we put into the system. So here's that ratio. And so now we got to figure out what this is. Because we know the network plus the heat loss is equal to the initial heat, that also means that the heat in minus the heat that's lost is the net work done per cycle. And so we can rewrite this way, and then it's not too hard to take the ratio of these things to appreciate that this is true. And this makes a lot of sense because you really want to minimize this heat loss, right? The worst possible thing is if all the heat that you put into the system ends up getting lost as to the ambient environment, to the air, whatever it's operating in, then this would be 1, and 1 minus 1 is 0, and your efficiency would be 0. So that would be your worst case scenario. But what we can do is we can use what we know about our thermodynamic processes to try to figure out how this relates back to temperature. So for example, in the constant volume processes, isochoric processes, if we're going from T cold to T hot, the amount of heat that it takes to do that, to go from this cold temperature to this hot temperature, is going to be the heat capacity times the number of moles. So and specifically, it's going to be the heat capacity at constant volume. And so we can replace Q hot with this expression. And really what we're doing is, maybe we already know how much energy is in from the laser, but we know that the laser is going to heat things up to T hot, so we can just use this instead, and that's fine. So we're going to sub that into there, and then in a second we'll think about Q cold, the heat that's lost because we have to compress this thing at constant pressure. So if this is the heat that it takes to get the system to go from, in other words, the air trapped inside of the piston to go from T cold to T hot, how much energy do we have to dump, and how does this relate to heat capacity for Q cold? So the first thing to think about is what the temperatures are, and we are starting from T warm, and we're going to T cold. So immediately, it's not too hard to figure out that these are the two temperatures we need to worry about, because the initial temperature in step 1 is T warm, the final temperature at the end of step 1 is T cold. So this is how much the temperature changes. And then there's some heat capacity involved in that. But here's the thing, is that it is not the heat capacity at constant volume, it's the heat capacity at constant pressure. And if you look in the book, there's specific heat at constant pressure. I think when you multiply it by the number of moles, it becomes the heat capacity. But so this is a slightly different number than the heat capacity at constant volume. And I'll talk about that in just a second. So again, this is our how much heat was involved in heating this stuff up from T cold to T hot in step 2. This is how much heat that we dumped in step 1. So we take the ratio of these things, we get something like this. Now the nice part about this expression is that we have the number of moles that is trapped inside of our piston here, and the number of moles that's trapped inside of our piston here. So that's going to cancel out, which is good. And so that leaves us with the ratio of the specific heat at constant pressure to the specific heat at constant volume. If you look in the book, this turns out to be equal to the gamma constant. Now, if I did some other gas, if I did, CO2 or N2, diatomic molecules or something, I would get something different for the gamma constant here. And so when you're doing the homework problem, I forget in my mind what the gamma factor is. But because I said we're using helium, we're going to use the gamma factor for the monatomic gas, which is 5/3. And so this is kind of a nice expression because we can convert this ratio to 5/3. So all I got to do is stick that into there. In general, it'd be the gamma factor there. And what I can do is I can, I think we're going to plot this up in a minute. But let's look at this for a second. This is the expression that we get for, again, this is for our 3-cycle engine, basically the simplest engine that I could think of. And we can compare this to the best efficiency from the ideal engine, which, as I said before, has 4 cycles in it. That efficiency turns out to be 1 minus Tc over T hot. And if you look in the book, it'll show you how to derive that. I'm not so interested in having you derive these efficiencies on the final exam. I'll talk about what I do expect in the final exam, but nevertheless, there are problems in the homework that involve calculating efficiencies, and so that's why we're going to talk about it now. So we can compare this equation, this result, to this result, and maybe you can already see that because of the 5/3, that this is going to be less efficient than this, right? So 1 minus some number over here that involves something cold over something hot, times 5/3, so this is going to be minus a larger thing perhaps than just this thing. And so what I can do is I can plot this up. I'll make some assumption for how much larger, T warm is from T hot. But at the end of the day, you get something like this. And so I'm calling my 3-phase engine the laser piston. That's the blue line. And then the green line here is the Carnot engine, the ideal efficiency. And as you can see, the efficiency is remarkably good. It's not perfect, but it's remarkably good. And again, I've just assumed something along the lines of that, like T warm is halfway between T cold and T hot. So you can see, again, Carnot is much more efficient. The moral of the story is that the simplest engine that you can think of is not necessarily the most efficient engine that you can think of. So maybe that's not too surprising in the end. But anyway, this is what you get. So one thing I want to highlight now going back just a few slides, is a question I want to ask is why does this say the network? Because we're trying to get work out of the system. Why not just say the work out of the system instead of saying the network, which implies that, I don't know, which maybe implies not all the work done is useful. Well, let's walk through this again. I've talked a little bit about the work that it takes to compress the piston in step 1 there. But let's talk about this. So again, which of these processes 1, 2, 3 involve work? So for example, step 2 here, does this involve work? Is there any work done? Is there work we have to do to the system in this step? Well, the answer to the question, was there work done, the first question you should always ask is, did anything actually move? In this step, in which the laser is turned on and the piston is pinned down here, has anything actually moved? Nope. I mean, the gas particles are zipping around faster inside of this thing, but that's not the kind of movement that we're interested in. We're interested in, does this piston move at all? And the answer is no. And if that's true, well, then the answer to whether work was done is really easy. It's like, nope, there's no work done. So again, if you look in the book, the work is the pressure times the change in volume. And here the volume is not changed. It's a constant volume process, isochoric. So there's no work done here. All we did was dump a bunch of laser energy into the gas and watch it heat up. Step 3, does this involve work? So again, the first question on your mind should be, well, does the piston actually move? It's a pretty simple answer to that one, yes. And the next question, if it did move, is, did it move by itself? Did it expand by itself, or did something have to pull it or compress it or anything like that? And if you think about the system, well, we heated up this gas, we let go of the pin, and it expanded out because the pressure inside of this thing was so big. We didn't have to pull it out. We didn't have to pull it this way. It just naturally did that because of how hot the gas was inside. So it expanded by itself. And so this is actually, you could use this to do useful work. So if you wanted to, I mean, honestly, the thing that comes to mind is like a t-shirt cannon. You have a t-shirt in there and then you launch something. The worksheet is actually on potato cannons. So if this was vertical, well, then I could use that as an elevator. I could say I could use this to, people could walk on board, or we could put freight on it and increase the height of it, and that would be useful work. But yes, you could use this to do something useful. Exactly what kind of useful thing you would do with this that's up to you. It's not my problem. But you could use this for useful work. So there is useful work happening in step 3. But what about step 1? Well, we talked about this before. Again, the first question is the piston actually moving? Well, yes, it is. Did it move by itself, or did we compress it? Well, we actually had to compress it. We had to shove this thing this way, and that actually took work. So this is work that we did on the system. It's not work that's done by the engine, it's work that is done on the engine, you could say. And so work happened, but it wasn't useful work. It was the drudgery of getting this back to the point where it's all set up for the laser to fire again. So it's working against the useful work that we did over here. Exactly how much work does that take? Well, it's a constant pressure process, so there's only really one pressure to worry about. I'm going to call that P low, because later on we'll talk about how when you get up here, that's going to be the high pressure. So it's a constant pressure process. The work done is the pressure times the change in volume. So that's P low times the change in volume. We're going to go from this big volume out here down to this small volume like that. And so that's the work that's done. And if we think about the work that's done in step 3 here, this is the work that we have to do to the system to get the thing to compress. Like, this is how much we have to shove it, force times the distance. If we think about the useful work that comes out of this step, that is a little bit tricky to determine, but you can trust me that this is how much work is done in this step. And so what I can do is I can, instead of doing all these ratios, what I could do is I could say, well, the net work is the useful work that comes out of step 3 minus the toil and drudgery that it took to compress the piston back to the point where we can turn the laser on. If you take those two things, stick them here, divide by Q hot, you will get exactly the same result as you got before. And so I just want to highlight that in this formula, if you forget about the work that it takes to compress the piston, you will not get the same efficiency and you'll get very confused. But if you remember that this is the net work, not the useful work, instead this is the useful work minus the counterproductive work, you could say, the toil. If you remember that it's the difference between those two things, then you'll actually get the same answer. Now again, in a real, say, automobile, we would allow the air to escape, things like that. Same thing with jet engines. Jet engines, the air is always coming in at some insane speed. So if you get in, if you guys are, some of you guys are aerospace engineering majors, you'll definitely get into that in your classes. The main advantage of just sort of letting the air escape is that then you get a much lower temperature. It's much easier to compress the piston again. So in real life, maybe we wouldn't use this thing. In real life, maybe we wouldn't use this thing, but in principle, it is possible. The other advantage of allowing the air to escape in a gasoline engine, conventional automobile, is that you've already burned a lot of the oxygen that was in the air before you put the fuel in, and so you need to have some fresh oxygen in there. Whereas for our laser piston, we don't really care about the fresh oxygen. We're just dumping energy into this thing with a laser, which goes right through the glass side of this thing. So we don't really care about adding new oxygen to the system. It's just, that doesn't have anything to do with the mechanism by which we're getting this thing to expand. So the next step would be to take our 3-cycle system and say, well, instead of adiabatic for step 3, why don't we make it isothermal? So again, we're going to be compressing it. So again, we're going to start from this big volume. We're going to compress it down. It's going to stay at this P low, this low pressure. So now we're at this smaller volume. Same as before. We're going to dump the laser energy in there to heat this thing up to the high pressure, same as before. But then in this third step, instead of allowing it to adiabatically expand, instead it will expand isothermally. And what's interesting about this is because it's expanding isothermal, isothermal is constant temperature. And so that means that the temperature that you start with has to be the same temperature that you end with, which means that this system only has 2 temperatures. It has T hot and it has T cold, so those are the only 2 temperatures. The other thing that this means is that this third phase has to involve the laser staying on. So you notice that the laser stayed on a little bit as it was expanding. So this third phase, to keep the temperature at that level, the only way that that's possible is if we keep the laser on in both step 2 and step 3. So these are the differences between my adiabatic laser piston, which we've been talking about, and the isothermal laser piston that we're talking about now. So we can analyze this, and what we'd like to do is figure out what the efficiency is. And it's not the simplest calculation in the world, but I'll walk you through it, and a lot of it's going to be the same as before. So in this phase 1, we need the gas inside of the piston to lose a certain amount of heat to go from T hot to T cold. Instead of T warm to T cold, it has to be T hot to T cold because there is no T warm. It's going to stay at T hot all through this phase. So that's a little bit different. but still overall very similar. Make sure to use the specific heat at constant pressure because we're staying at constant pressure here. And then we're going to add heat in step 2. So step 2 is the same as before, but now we're going to add heat in step 3. That's the new thing. And to add heat at step 3, that means that the heat that we add is going to be the same as the work that's done by the system. In other words, to keep it at this temperature, we have to add this much heat into it. We talked about this last lecture of what is the work done. What is the work done in an isothermal case? Well, to make that work happen, we have to add heat to the system there. So that's going to complicate things a little bit because now when we go to the efficiency, QC is still pretty simple. There's only one part of the system that we're sort of intentionally losing energy. But now Q hot is a little bit complicated because there's 2 different steps when we're adding heat to the system. There's the heat that we add in step 2 when the laser is turned on in step 2, and then there's the heat that we add in step 3 because the laser continues to be on in step 3, which again is different than before. From before, we were just letting it expand with the laser turned off in step 3. But we can use this to calculate an efficiency because we know what QC is in terms of the temperatures, and we know what these are. So QC is this, as we talked about. QH2 is that, because that's constant volume process. We're just heating up the gas with the laser. And then the heat that's involved in step 3, as it's expanding, is like that. This actually simplifies to some degree because we have the moles, the number of moles in each part of this, so the number of moles cancels out, which makes it a little bit nicer. And I think there's one more simplification that we can do. If you think about the ratio of Cp to Cv, R is this gas constant, the 8.31 joules per mole Kelvin, stuff like that. So I forget how we're going to simplify this. I think the next thing to think about is what to do with this ratio of the volumes. And how does that, and because it would be nice if we can relate this back to temperature so we can get something that only depends on the temperature. Okay? So I think that's what we're going to talk about next. Going from here to here, this ratio is 5/3. But Cp itself is gamma times R. Cv itself is just R. And so we can divide out by R, and so you notice that the R disappears here. So now again, the last step is to try to figure out what to do with this ratio of the volumes, which we're going to do in the next slide. So I can also rearrange this a little bit in terms of factoring out T-hots and things like that. All right. But let's think about this ratio of the volumes here. So there are 2 different pressures and 2 different volumes essentially in the system. I mean, it goes from one to the other, but there's kind of 3 points that we care about, and there's only 2 different volumes for those points and 2 different pressures. Remember what I said earlier, the ideal gas law is true for everything in this whole unit. The ideal gas law does not break down, which means that if you think the ideal gas law is true here, it's true here, and it's true here. And it connects to the pressure, the volume, and the temperature, which means that the pressure here times the volume here at this hottest phase is equal to nRT, right? Remember the chemist's version of the ideal gas law? So that's this. And those things multiply together, and the temperature at this case is the hot temperature. We can also write down the ideal gas law for this case and this case. So the next one, I'm guessing, is probably going to be this one. So that's going to be P low. So the next one's definitely going to be P low, and then maybe V big. Yep. P low times V big. And because it's isothermal expansion, then that is still equal to T hot. We expanded, but we kept it the same temperature. And then the last one would be T cold here. So that's going to be P low the low pressure, times the low volume, and those things multiply together to get T cold. And so this is, so these are what we get from the ideal gas law. And remember, our goal was to try to figure out the ratio of, say, V big to V small in terms of not the volumes, but in terms of the temperatures. And so there's a variety of different ways of doing that. I think the easiest one is take these two expressions and just take the ratio of them, right? So, because P low is the same for both of them, and it tells you that the ratio of V big to V small is going to be the ratio of T hot to T cold. And so I can take our original expression like this and stick in this, right? Because this is the only change between these two things is that. And then I can go and, I can plot it up, for example. And you find that the isothermal laser piston, again, is not quite as efficient as the Carnot engine. But it's more efficient than the adiabatic laser piston. There's something about isothermal processes that makes it more efficient that I'm still wrapping my mind around, to be honest. But in any case, we got to the finish line. We figured out what this efficiency is as a function of temperature. And we, again, the simplest engine, one of the simplest engines we could think of, turns out not to be the most efficient engine that we can think of. So there you go. Now, in terms of the worksheet for today, it's pretty fun, I think, because it talks about potato cannons. I don't know if any of you guys have potato cannons at home, but in my mind, this is a process that has this is a sequence that has two processes in it, and that's what I expect you to be able to do on the exam. I expect to be able to tell you that there's this process and that process, and then you can tell me like what the final temperature is and the final pressure, things like that. So in this first phase, we're going to pump a bunch of air into this container, this part of the potato cannon, until it's very high pressure, and then we're going to let it go, and this thing is going to the sealed part of this thing is going to expand. So you can imagine there's like a plunger at the feet of this potato cannon. If it was a real potato cannon, then you kind of have to use the potato itself to make that seal. But in any case, this thing is going to expand out, and we need to figure out what this final pressure is as the potato is leaving, because that can help us figure out what the average pressure was, which can help us figure out what the average force was, which can help us figure out what the velocity of the potato was as it was leaving the potato cannon. So that's the worksheet for today. I hope you enjoy it. And again, I think it's a reasonable prep for the exam. So hope you enjoyed this lecture. I'll follow up with a review of what's going to be on the final soon enough. But you've made it through all of the new content for this course. The only thing left is the review. So thanks for watching, and I'll see you guys soon.